Hello, and thank you for joining us for this Comau webinar with Automotive Manufacturing Solutions. I'm Nick Holt, Editor of Automotive Manufacturing Solutions magazine. Today we welcome back Martin Kinsella, who is Director of Advanced Materials and Process Technologies at Comau. During this webinar, Martin will discuss the challenges facing the industry as it rapidly moves towards the use of advanced lightweight materials in body enclosure systems. Now, before we start, I'd like to remind all of you in attendance to draft up some questions which Martin will be pleased to answer in the Q&A session following the presentation. You can ask these questions by typing them into the box in the lower right-hand side of your screen. And if you should happen to experience any technical issues during this session, please also type these into the Q&A box, and our team here will do their best to sort these out for you. We hope you'll find this webinar stimulating and informative, and I'll now hand over to Martin to begin the presentation. Thank you.
Thank you there, Nick, for that introduction. Good morning, good afternoon, and good evening to wherever the listeners are in terms of the webinar. Much appreciated for the opportunity to speak today on advanced materials and technologies associated. My name's Martin Kinsella, as Nick said, Director of Advanced Materials for Comau. Been with Comau approximately 24 years, and what we'd like to do this morning, today rather, is just show a number of slides in terms of some technologies that are new to the marketplace, some of the manufacturing techniques used in the body and white industry, and also some of the new processes, and also not so new processes, but maybe more increased in terms of volume and manufacturability, etc. Okay, so why are we meeting today? Well, as we all know on the line, I'm sure, there's a global drive in terms of the CO2 emissions, or CO2 challenge, as some people say. The 2025 international target across the world, being driven by all countries, is, let's say, dictating and ensuring that the OEMs across all nations and all manufacturers are gearing themselves towards the target. For example, the 2025 figure, for example, in the US, 54 miles per gallon, is causing, let's say, a lot of interest and driving a lot of new technology and new advancements in materials, etc. If we look at as to why, if we look at the new materials and new processes, we're kind of looking at a body in white assembly where if we were able to reduce the mass by approximately, let's say, 8 to 10%, that can then give a fuel economy saving of maybe 3 to 4%. So those initiatives are kind of driving the industry to look at every process, every product, every material that makes up not only the body in white but the whole vehicle, to try and look for new and innovative solutions. So part of that is kind of driving the industry to maybe not move away completely from the traditional steel, but what is driving the industry, both in terms of OEMs and also in terms of manufacturers, is the fact that we're now going to be looking at multi-material, multi-processes, and these are driving the, let's say, for example, the suppliers. Steel industry, for example, are now investing heavily in new materials and new steels that are lighter, stronger, are more, let's say, give a great crash test results, but their mass is actually reduced dramatically. There's a lot of talk in the industry currently about aluminium. Again, this is in terms of its weight saving compared to steel. Maybe there's about a 20 to 30% weight saving against traditional materials. So this is again driving the industry to look at aluminium. But there are other materials around that are becoming more and more commonplace. For example, magnesiums, carbon fiber, reinforced plastic, etc. And these are becoming part of this multi-material combination that's going to help the industry meet their targets of 2025. If we look on this slide, for example, what we're doing, we're depicting some of the materials on the left-hand side in terms of the processes. So we've got aluminium, composites, plastics, and steel. But then I break down steel into a number of different components, because the steel industry now are really looking and targeting the mass of their materials, and this is kind of driving some new materials into the marketplace. So we've got dual phase, we've got trip and TWIP, etc. These are materials now that are kind of being developed that are dramatically lighter than traditional steels, but the megapascal values now are approaching 16, 17, 1900s. So what that does, it's kind of driving in terms of a process to join those materials and technology, driving the joining techniques to a greater level of technology. And what that's doing, it's obviously driving new solutions into the body shop. On the right-hand side of the slide, you can see just a small selection of the current joining processes that are around currently. So, for example, resistance spot welding, been around for several decades, etc., and the mainstream technology being used in the body in white. But now it's becoming integrated with other technologies, such as self-pierce riveting, flow draw screws, laser welding, adhesives, gluing, bonding, etc. So now we're getting into an environment where the actual body in white structure has not only got multi-materials, but it's also got multi-joining processes. And this could be in, let's say, for example, where traditionally we'd have a body shop maybe solely on resistance spot welding. Now you're actually getting body shops where within a single station or within a single line, you've got resistance spot welding with other processes. Could be adhesive, maybe another station's got self-pierce riveting function with flow draw screw. So what that's driving the OEM and the let's say the supplier base to do is to develop processes that are robust, that are repeatable, that have, let's say, improved mean time between failure, mean time to repair, so that the overall solution of the facility can meet these new technologies. And what that's doing in turn is actually then driving the both the OEMs and the suppliers to look at different technologies in different locations. So here we have on this particular slide, we have a number of technologies where in the commonplace in traditional steel facilities, so for example, resistance spot welding, adhesive, laser, MIG welding, these are technologies that have been around for a long period of time. They've been well incorporated into low, medium and high volume manufacturing facilities. But now with the evolution of the other materials, such as magnesiums, aluminiums, carbon fibers, etc., that's now driving these solutions to develop and evolve into a total solution whereby the introduction of new joining technology to cater for these new materials. Now, some of the technology, for example, if we look at self-pierce riveting, it can join large spectrum of materials, but it's not new in terms of the marketplace. It's been around for decades now, but it's becoming more commonplace. It's becoming more widespread in both a low and medium volume and also in high volume locations. So, for example, also flow draw screw. Again, it's been around for quite some period of time, but what is now being utilised is in a large number of OEMs across a large number of programs and continents, and it's being incorporated not in an isolated area of a vehicle, but more commonplace maybe in terms of the underbody and the upper structure. So that's then driving us as a technology supplier to look at these technologies, to look at how they're incorporated into a facility and into a process, so that we can then evolve, test, and make sure that the overall solution is a robust solution. What the next slide shows is we're just depicting some of the growth rate in terms of both the jobs per hour. On the left-hand side, you can see the jobs per hour depicted, the technologies, the various technologies, and this is just a small selection of the technologies and how they're being used, and how you can see the trend over the last number of years. It's kind of gone from low volume manufacture, 20 jobs per hour, incorporating a couple of technologies, up to the last number of years where now we're getting to 50, 60, 70 and 80 jobs per hour, incorporating a large number of different processes in the same body. So what this is trying to show is that the focus of attention of the industry is changing, and also the focus of attention in terms of the manufacturability of the different processes. So whereby you had one or two isolated technologies within a solution, now you have maybe 3 or 4, 6 or 8 different solutions inside a single body. But what this is doing, this is enabling the OEMs to meet their targets. So by incorporating the different materials and different products, they're driving their mass down, they're improving their fuel economy, and at the same time they're able to, with, let's say, creative design, improve the safety structure for the actual vehicle, reduce in terms of the overall mass, which is improving their economy, but are also the increased use of the materials. That's also driving a cost reduction in the marketplace. A number of years ago, one or two of these materials were deemed to be way beyond the mass volume market because of their initial costs. But because of investments and demand across the world, this has driven the cost down dramatically, whereby these certain materials are now becoming, I don't say widespread, but they are becoming more commonplace in the overall vehicle. So if we look at magnesium, for example, 20, 30 years ago, it wasn't very common in terms of the solution of a product within the overall vehicle, including body weight, powertrain, etc. But now it's becoming more widespread in terms of particular engine mounting, different technologies, etc. across the marketplace, which is helping the OEMs meet their targets. The next slide just shows a typical example of whereby a typical process that was used in the marketplace, which is flow drill screw. Been around for several years. It's been used in a large number of OEMs more recently. But what we're depicting here is that with the introduction of the technology into a medium and high volume atmosphere or marketplace, we as the industry are having to really robustly look at the actual processes. We're having to look at it in terms of the maintainability, look at it in terms of its uptime and its efficiency, because the introduction of new materials and the introduction of new technologies are introducing, let's say, some unknowns. And what the industry are doing is actually meeting those unknowns and trying to eliminate some of those risks, whereby intensive testing and manufacturability understanding of the technology and how the materials are reacting is being taken place to help and assist this throughout the product development. So, for example, here we've just kind of got a test facility where we're looking at flow drill screws. We're kind of doing various testing. We're looking at speeds, angles, screw definition, screw hardness, screw coating, etc. And these are all small pieces on their own, but together it brings a complete solution. If one of those particular small pieces, for example, the coating of the material, the hardness of the screw itself, is not to quality, well, that'll give a production and joint integrity issue, which of course is a major concern. So that by testing it exhaustively in various angles and various approaches, we've been able to develop a very good understanding of this process. So we're able to ensure that from a confidence point of view, the OEM can look at this product and this solution and use it in a higher volume application. Whereas maybe 10 or 20 years ago, it was seen as a potential risk and seen as, let's say, low impact and not a worthwhile technology. But now we're actually able to, let's say, single side join multi-materials robustly and securely, given a good joint integrity for the actual product. So this is just an example of whereby the testing and development is you could say, are equally or even more important than the production environment, because this gives a very good understanding in terms of the component parts, the application and the technology used to apply those component parts. This slide is just some of the, let's say, strategies in terms of the manufacturing environment in different OEMs across the globe, why they're looking at different strategies and where they're trying to drive towards is that's driving the industry to kind of come up with different solutions. So all OEMs around the world are looking for model architecture and flexibility. This means where they're able to actually take, it could be multi-variants in terms of vehicles, it could be cars and trucks down the same line, it could be different variants of the same vehicle being built down the same line, so to increase the flexibility and the utilization of the actual facility. Engineered logistics, again, another example whereby the factory and piece part flow not only into the factory but the surrounding area is a key part. Volume flexibility, making sure that volumes in terms of the production rates can flex up and down as and when required, and also to ensure that the demand for new vehicles, there's a ability there to actually increase demand at, let's say, relatively short notice, and this then is meeting the customer demands. Compressed timing across the whole industry. Timing is everything. Timing is the key driver of the industry. So timing to meet 2025 is obviously one key component, but timing to meet launches, to meet the customer demand for, let's say, quick model turnaround, quick model changeovers, facelifts, complete different variants down let's say, an existing facility. This is driving the timing to be very short over there in the recent years. We mentioned about diverse materials and joining techniques within the same body shop is now becoming commonplace. Building structure, and then also global support. All the OEMs now are operating on a global basis, which, from a Comau perspective, you know, us being an equally global company, is working quite well, where we're able to support, let's say, the global demand in various locations. And the customers, the OEMs, are looking at global operations, so they're manufacturing the same product in Asia as they're manufacturing in Europe, manufacturing a different model in South America that they're operating in China. So the OEMs are also driving across common platforms, common structures, common design, so the solutions to actually meet these market drivers is a big need in terms of manufacturing. And what we're actually doing at Comau is we're actually coming up with let's say, a manufacturing strategy, a Comau solution, where we're looking at the demand from the OEMs and try to understand the different drivers. We're coming up with a Comau Flex solution, and what this does, it's a comprehensive product-driven, flexible manufacturing strategy, and it's solution-focused as opposed to component-driven. So we're actually kind of looking at the complete body shop solution and not just a component part, maybe the rear quarter, the left inner or sills, etc. We're actually looking at the complete body shop. And what we're going to do, we're going to run a short video now just to kind of show you some of the technology we're referring to. What we're showing here is just an overview of the facility, a general layout. Now we're going into the actual facility. And what we'll show is we can actually show you where we've actually got the facility laid out in a certain structure, in a certain methodology, strategy, in terms of aiding the maintenance personnel and production flow. Built up by two main transfer systems, Versa Roll and Versa Pallet, which are high-speed transfer systems, Comau patented, in a very modular approach to the body shop. And as you can see, the material flow and assembly zones are separated. What this does, it We have a slide later on which kind of goes through a little bit more detail. And what we're showing here is a single module. You know, we refer to it as a brick, basic robot integrated configuration, where we have the configuration of the line is clean and straight to allow maintenance accessible and, let's say, areas where maintenance can easily get to work on the particular facilities, etc. You can see here in terms of the approach to the facility, it's structured, it's laid out cleanly, it's in a logical flow throughout the facility. We have different standard products which then incorporate and bring into a complete body shop solution. And then these can then be broken down also into smaller sub-assembly areas. So what this is actually giving the customer the flexibility and the solution that he needs. We've been looking and engineering this factory for some time in terms of approach to the solution. So as you can see, left-hand side was just a modular concept in terms of a body shop solution. We have what we call key enablers in terms of development processes. So this is trying to meet those critical areas we mentioned earlier. Flexible, modular tooling, sequences, part delivery, installation, solutions, etc. To the right-hand side where we've got the complete body shop solution, where it's a safer environment, improved logistics, and reduced footprint in terms of the overall body shop solution. This is made up of a number of enablers. So in terms of flexible tooling to meet the customer model variants, trucks, vehicles, cars, etc., two-door, four-door. We've then got other solutions in terms of conveyancing, logistics, flexible manufacturing in terms of the management, so that's scheduling and logistics. We mentioned in the video in terms of the brick, so basic robot integrated configuration. So each station is made up of the modules. The modules are bricks and condos. The transfer system could be a Versa roll or Versa pallet. But what we've done, we've driven an engineered solution here where the product is a piece that goes into the solution. The actual solution itself, is an engineered solution. So it's engineered robot placement, engineered in terms of its shipment and installation, and we'll show a short video of that shortly. Engineered in terms of panels, cables, etc., that all make up a facility. But because it's pre-engineered, we're able to produce, let's say, like a standard product. This is enabling us to reduce time frame in terms of manufacturing and installation, but also in terms of engineering and working with the customer to give a complete solution to their body shop. It's made up of two main variants. We've got the Versa pallet system. You can see at the top of the slide there, and the lower area we've then got the Versa roll. So you can see the two solutions. One is a pallet system. Again, it's a pallet to deliver the underbody, which has then got the body sides and framed vehicle, and then the carrier can produce the underbody, body sides, and other sub-assemblies. Top area, up to 14 robots in general station. We'll show you an example shortly on the video with 18. And then in the robot Versa roll, we have up to approximately 8 robots. We mentioned about the OEMs having to have flexibility, not only in terms of their model mix, but also in terms of volume. So what this solution is being able to develop is that we're able to make it scalable. So we can actually install a system that maybe has 8 to 10 stations to meet a particular volume requirement initially. And then as the program and the volumes increase, we can then easily, as you can see demonstrated here, we can extend the actual production environment. So we're able to increase the volume for that, utilizing the same equipment and then more standard products. So this enables the customer to then actually increase his volume with relatively low risk in a very short time frame. So he's able to move and flex his body shop to suit new requirements from the customer. Part of the process is in terms of high density joining. So what we have here is a short video showing a framing station whereby 18 robots, fully integrated, fully, let's say, virtual world engineered, then into the real world, where we're doing approximately 90 spots on a process time of approximately 47 seconds. So we'll just run this short video. Here you can see the actual, we're loading on the body sides onto an underbody. We've then tabbed the body together, so we've now got the tabbed vehicle. Okay, and we're approaching the framing station then, where we're actually, the engineered solution, as you can see, we've got floor-mounted and gantry-mounted robots. There's 18 in total. Pallet system then drops down and is clamped up. We then have a large number of robots applying approximately 47 in 47 seconds, about 90 spots. So what that's then given is very high flexibility, yeah, and also from a point of view of the solution, it's flexible in terms of the approach. It's, in this particular instance, it's resistant spot welding, but that could be self-pierce routing, could be flow drill screwing, etc., or a combination thereof. Next slide then, we talk about sequence part delivery. We have at the top a conventional and traditional approach to the line and feeding of the component parts. So it could be being delivered by power and free, accumulating conveyors, rack unload areas. And as you can see, they're situated throughout the complete line. Yeah, so there's some at the top, there's some at the lower edge, there's some to the start of the line, and some to the rear of the line. And what that then does, it actually gives you a large number of breakpoints into the actual process flow. And each time there's a breakpoint, there's a potential for a risk. So there's potential for breakdown, there's potential for access issues, etc. Whereas the Comau Flex solution and sequence part delivery, the complete solution works out that we load component parts into the first two stations. These first two stations then focus the attention in terms of component delivery, but also in terms of breakpoints into the line. What this then does, it gives improved mean time between failure, mean time to repair, because we've got less feeding parts and less conveyors. Yeah, we've got, let's say, product architecture is independent because we can load on at the first two stations. And then, as you can see, we've clearly shown in the actual process flow, the parts are then taken from the carrier into the actual assembly by the robot. So what this is now doing, we're utilizing the dead carrier to carry the parts, as opposed to maybe a conveyor that has various switches, various mechanical items, cylinders, etc. So we're able to reduce the component parts, so therefore improve the overall reliability of the actual system. Here we've just got a body shop view where we're showing the actual material zone. So we've got trucks pulling up to the lower edge of the actual facility. We then got what we call the material zone, where we actually have the sub-assemblies and the logistics piece flow. And then that then loads on, as we said earlier, into the first two stations of the assembly zone. So now we've actually broken the factory into key areas. Clearly, part loading the minor subs, main line and major subs, and then ship to paint. And what this then does in terms of the operators, it's actually, in the maintenance areas, it's actually reducing the amount of traffic flow in terms of fork truck moving. Fork trucks are only focused in this area, the sub-assembly area. Production is again only focused in the lower area in terms of the marketplace and part loading. And the maintenance are in the upper area, whereby they have clean, structured lines to work on with good visibility, and there's no danger of fork trucks or any other potential risks for the maintenance personnel. So by reducing the fork truck flow, again, only seen as maybe not as a major item, but it is in terms of reducing the risks in terms of accidents, reducing the risks in terms of emissions and fuels, etc. But it's also giving the clean access to the manufacturing facility. One of the critical drivers we mentioned was time. So with a conventional body shop, you go through stages of engineered solutions, so design, build, install, commission, etc. But with the modular approach, in terms of the Comau Flex, we're able to actually reduce that design time because we're using a standard component, standard products. So what we're able to do, we're able to launch those products early on in the engineering phase because we know the approximate line configuration will dictate a certain number of standard components, so we can launch those to manufacture. And then working with the customer specifications, we can then incorporate those into that solution. Whereby if we have a Comau Flex strategic relationship, this is whereby working with the OEM in terms of standards, common standards between the solutions, looking at optimized standards in terms of controls and mechanical design, etc. This can be reduce the time down even further, which gives an overall benefit to the complete program, saving time, saving cost, and saving investment for the customer, which are obviously key drivers. Part of that modularity and that approach also improves in terms of installation. So because we have let's say, a standard solution, we're able to incorporate, let's say, techniques in terms of its installation. We're able to come up with what we call mega leg solutions, where we actually have component parts. We actually, as relatively as easy as it sounds in terms of the installation of the floor plates can be quite time consuming. So what we've done here, we've actually modified the overall design, come up with a solution whereby we can actually stud and fix all the floor plates at once. So this gives a small saving, but when you're applying 1,000 studs, you can see the impact can be quite significant across a body shop. Here we have just some couple of pictorials showing floor plates being installed. The legs are then being installed. The bricks, the shipping modules we spoke about are shipped as one, where we have the robots mounted to the brick, the cabinets and the control cables and pipework, etc., are all in one module, and these are put onto a truck and shipped to site. And then we have the complete solution installed. I'm just going to run a short video now showing let's say, the solutions being installed. This was actually at the Detroit Motor Show earlier this year, where in a very short period of time, due to the structure and nature of the actual modular manufacturing processes, we were able to deliver a 6-station facility in less than 3 days, and that was from install to power up, which in the current industry is remarkable. But as you can see, because of its very nature in terms of its building blocks, this is a very quick modular approach. Similar to, let's say, Lego. We're just building two blocks, 3 blocks, 6 blocks, or 50 to 60 blocks. This then will just show you a little bit longer of the video where we're actually doing the floor plates, and for those who actually were lucky enough to go to the motor show, it was a very different stand and a very different assembly process shown to the marketplace. So, manufacturing future trends. Every manufacturer and every OEM around the world, yeah, they're all focused and being driven in terms of their targets, in terms of the achievement of their CAFE standards through utilization of various materials. Yeah, and this is driving the industry, not only the OEMs, but the first tier, second tier, third tier suppliers, and the component and commercial component suppliers, to come up with cost-effective solutions that are, let's say, driving and ensuring from a low risk point of view, the risk in the marketplace of the high volume environment is being reduced. So as not to kind of try and introduce a new technology or a new product or a new material into a high volume atmosphere or a high volume requirement with no testing. Greater focus in terms of the customer now in terms of a system approach to vehicle design as opposed to smaller component pieces. Characterization of material properties. This is a key area of focus in terms of joint integrity. In particular, for example, when we're joining the high-strength steels or the various grades of aluminium, looking at the actual the heat treatment, looking at the thickness and the coatings, etc., the actual materials, but ensuring that we understood to ensure a robust joint in a high volume manufacturing area. Interaction of different materials in similar processes, a wide variety of manufacturing techniques. Absolute key is the virtual 3D design and simulation, ensuring that everything's tried and tested in the CAD environment before going into the manufacturing environment. And then, of course, an increase in terms of manufacturing testing. And there on the right-hand side, you can just see a typical breakdown of a vehicle with just in terms of its vehicle structure, everything from mild steel to ultra-high strength hot form steels to aluminium and other components. And that's just a typical OEM vehicle now made up of those various materials and the various component parts, which is becoming more and more commonplace in the medium and high volume manufacturing. Us at Comau, we're ensuring this, let's say, drive by ensuring that we have a comprehensive strategy that focuses on the combination of the various design principles and capabilities to join. We say premium materials, but nowadays they're actually becoming more commonplace, such as aluminium, advanced high-strength steels, press-hardened steels, carbon fiber, composites, plastics, etc., are now becoming more commonplace. And here at Comau we're doing, let's say, a large amount of testing within our technology centres to actually ensure that we can deliver a high-volume, low-risk application and solution to the customer. So that concludes the presentation. We'll open up now to some questions and answers, and hopefully you've found it informative and constructive. Over to you, Nick.
Thanks, Martin. Really interesting presentation there on the future of lightweighting vehicles. It's a really hot topic at the moment. We do have some questions for you. I'll start off. One of our attendees wants to ask you to clarify the term JPH in production rate and joint mix trend. Jobs per hour.
So JPH, that's jobs per hour. So what that means is the amount of product produced within a given time frame. So we showed in one of the earlier slides where the jobs per hour had kind of increased from maybe 15 to 20 jobs per hour up to 60, 70, and 80 jobs per hour in terms of the high volume manufacturing process. And what that means is that the volume throughout the body shop to achieve that target is part of the overall solution. And that also plays well into the next kind of subject, Nick, where by looking at the jobs per hour requirement of X, let's say it's 60 jobs per hour, if the solution can be have greater uptime, can have improved mean time between failure, mean time to repair figures, and has an increased technical availability, by design, you actually design a facility or a solution to give a gross of maybe 2, 4, maybe up to 8% greater volume than the requirements, because you're actually accounting in your simulation for downtime, for breakdowns, etc. But if you can make a solution that actually has a greater technical availability, you can then maybe reduce that, let's call it the buffer or the risk factor, by 2 or 3%, which may not sound a lot, but if you've got an area, for example, maybe with between 500 to 1,000 robots, you may be operating on the floor space of 600,000 square feet. If you can reduce that area and that content down by 2 or 3%, then you're actually making a significant difference to both cost, timing, and content. Okay.
Thanks, Martin. Question here: is Comau developing a robotic FSW solution, a sort of friction stir welding solution?
We have worked in the past on a friction stir solution. Currently, we're evaluating a number of different joining techniques, of which that is one particular solution.
Thanks, Martin. Sorry, carry on.
No, I was just saying, like I said, we're currently, let's say, evaluating that as a potential opportunity.
Because there are a few OEMs out there who are we're starting to see increased use of that now, I suppose, now with obviously with the multi-mix materials that we're seeing. A question we've got here for you, Martin. What are the current developments being made to the process auto die change in SPR applications to reduce high investments in gun equipment?
Okay, well, there's a number of SPR supplies in the marketplace, of which having automatic die exchange is, let's say, a very good initiative, because then what you're able to do, we mentioned earlier about the engineering the solution, so you're able to get to a greater utilization of the actual SPR, the gun, which is, let's say, a high value component of the body shop. And by having auto die exchange, you can then take the same C-frame with 2 or 3, let's say, die configurations on the same C-frame, rapidly changing the dies, giving greater flexibility to that gun or that C-frame, and therefore being able to increase its utilization. Because in a body shop environment now, and for some time, is the actual robot which moves the end effector, for example, the self-pierce riveting gun or the resistance spot welding gun from A to B. The robot, in terms of its cost, has actually, let's say, dropped dramatically, whereby it's now seen as a lower value asset than the actual end effector, than the gun itself. So maximising and utilising those high value assets, sweating the assets, as it's sometimes referred to, as in the self-pierce rivet gun, is a key component to the body shop solution. So automatic die exchange is a good initiative and becoming more widespread.
Thanks, Martin. Question here. Can you explain process testing with regard to flow drill screw operation?
Process testing. So flow drill screw operation has been around for a large number of years, seen as a viable solution for single-sided joining in various materials. Okay. In terms of process testing, what we look at in terms of the actual the manufacturing testing solution is various things. So we're looking at speeds and feeds of the actual screw into the component parts. We're looking at approach angle. We're looking at, let's say, can we apply the screw off perpendicular, maybe by 3 degrees or 5 degrees. What impact that has on the actual joint configuration. Manufacturing ability to deliver the screw over a repeated period of time in a high volume atmosphere, so making sure that screw delivery to the spindle is robust, making sure that the actual, again, the screw itself, the key component in terms of its hardness, its coating, its thread formation, its head design and configuration, making sure that's also well thought out and well engineered. So they all form part of the process testing requirements.
Thanks, Martin. Question here. Are you seeing an increase in plastic or fibre-filled plastic components used for lightweighting?
Absolutely. It's now those component parts are becoming mainstream. Yeah, in terms of if we look back only a few number of years ago, plastics or carbon fiber reinforced, etc., were seen as exotic or seen as utilized only on, for example, Formula One racing cars, etc. But that technology is now becoming more mainstream. Plastics now, in terms of the interior of the vehicle, and also some of the body mounts and body structures, are definitely becoming more commonplace. Things like simple things. If you look at the fuel filler, good example now. There's a component part. It's relatively small. It's very low risk, but there's a weight saving now gained from where the fuel fillers now manufactured from a plastic component. The carbon fiber reinforced plastics, again, seen a number of years ago only as being utilized very high-end niche vehicles, Formula One, etc. You're now seeing in some of the mainstream vehicles that being utilized in various areas of the body, so as to dramatically reduce the weight, because its weight saving compared to other components is significant. And also with the increased volume of the actual or the volume demand, that's at the same time driving down the cost. So before, the cost was just wasn't feasible in terms of medium to high volume manufacturing, just purely because from a cost point of view. But now with the demand, the costs have been reduced, and it's becoming more mainstream. It has also got some development work in the industry in terms of looking at it from a recycling point of perspective.
Thanks, Martin. Question here about lightweight spot welding guns. Where do you find use of these in today's market? And the subsequent question to that is, what's Comau's compatibility or availability, I'm not sure, in lightweight spot welding guns?
Okay, so resistance spot welding has been around for a long period of time. Resistance spot weld of lightweight components, aluminium. Again, it's quite interesting reading the looking at the press and the different information around nowadays. It's like as if it's only just started, but there's been closure and component parts such as hood and deck and doors, etc., utilizing resistance spot welding with aluminium for a long period of time. So it's becoming more and more widespread and spreading out also from not only from closures but into other areas of the vehicle. In terms of Comau, yes, we manufacture our own welding guns. We have a significant amount of guns currently on the marketplace that are being used in volume manufacture and utilizing or being utilized on materials such as aluminium. And there's also been in the marketplace and the industry significant developments in terms of timer controls and let's say adaptive control in terms of resistance spot welding, which is now let's say enabling the industry to look at these materials in a different light, because the adaptive control now is becoming so sensitive and so, let's say, effective in its performance that it's not seen as such a major risk as it was previously on some of the traditional weld timer controls.
Thanks, Martin. We've got time for just a couple more questions. This one's a sort of a two-parter. Has the Comau Flex system been installed at any OEMs yet, or is it just a concept so far in terms of an entire line? I think the question is.
Okay, so we showed in the video and also in the slides two component parts, the Versa roll and Versa pallet, and yes, installed in several OEMs around the world, utilized in, let's say, a number of vehicle size manufacturing, from smaller, let's say, saloon cars up to larger vehicles and trucks, etc., and across a large number of different continents. Yeah, We also showed there the open gate where we had the 18 robots. We've got the open gate solution in over 100 different applications in different OEMs around the globe. So to answer that question, yes, and in several areas, and also up to significant jobs per hour, up to and including approximately 80 jobs per hour with approximately a four model variants.
Thanks, Martin. Second part here from the same attendant. In terms of calendar weeks, how much time do you expect to save in comparison to a conventional solution from SE planning to job one?
I think I'll have to answer that from a point of view, let's say, it would depend upon the component and the customer. Yeah, we work with different customers in terms of our approach, in terms of SE, engineering, etc. The time frame to save can be multiple weeks because we can actually launch standard components in the simultaneous and engineering phase at the very start, as opposed to waiting until the SE is maybe partly or completely delivered, and then you would then go into your layout work, etc. So the significant time saving in terms of the engineering and the manufacturing solution, multiple weeks, and then also in terms of the actual installation time, because of its modular build and modular approach, we can significantly reduce the installation time. Nick, that would depend upon the size of the facility. If it's a single line, that can be reduced by several days. If it's a complete body shop, it could be reduced by several weeks. So it's really dependent upon the customer scope of work and the volume mix and the volume requirements. But utilizing the approach in terms of the Comau Flex, significant time savings in the engineering frame, in the manufacturing time frame, and also in the installation time, which then, of course, you launch across the SE to job one time frame is multiple weeks. So it could be, depending upon the program, maybe as much as 4, 6, 8 weeks, if not more, depending upon the actual program and the customer requirements.
Thanks, Martin. Well, we can almost let you go. I've got time for just 2 more questions, if you're okay with that. Question here, what solutions does Comau offer or recommend to join high-strength steel to aluminium?
Depending upon the component parts, and I'd rather not say a particular defined process. I'd rather say that we'd look at the materials, we'd look at the stack up, we'd look at the combination of the direction in terms of the process, because that's one of the key areas in terms of engineering, Nick, where with the different and multi-materials, now the engineering has to be detailed. It has to understand the materials, the hardness, the coatings, etc., how they're going to react with each other. So, for example, it could be, if it was looking at a particular design, it could be self-pierce riveting. But in terms of the engineering solution, we then have to look at, for example, what's the megapascal of the material? Yeah. So, for example, it could drive a different rivet combination if it's one particular strength, or if it's another strength, it would drive maybe another rivet combination. So it's the questions now, because of the joint integrity being the key component part of the vehicle, yeah, how that joint's made up is the key piece of the engineering. So rather than just say it would always be a rivet, it would always be a flow drill screw, or it could be in terms of potentially another joining process. It's much better to understand the exact component parts before actually just saying it would always be this solution.
Yeah, it's a tricky one, that one, Martin, because as you say, there are a lot of elements to consider with that kind of thing. And obviously anyone who comes up with a very simple solution to that sort of joining issue is going to be a very rich man or a very wealthy company. Anyway, last question here for you, and looking at something that's been in the news quite a lot. A question here regarding BMW and the I-Series cars made of composite. It says here, obviously, the most of the joints are adhesive; they're glued. Is Comau looking at providing a solution for this kind of joining method?
Yeah, absolutely. And I mean, we've worked on many solutions, many OEM projects whereby the utilisation of adhesives has been exponential over the last number of years, particularly related to aluminium, where the utilisation of the actual adhesive in the component parts and the body in white has gone from maybe, certain vehicle manufacturers from maybe 10 metres per vehicle up to something maybe 100, 120 metres per vehicle. So yes, we have utilised a large number of adhesive applications. We've worked closely with a number of adhesive manufacturers and dispensing technology. It's a great area of growth in terms of the industry because now the actual bond strength for the materials available today and tomorrow are significantly higher than they were a number of years ago, and also in terms of their effectiveness in both, let's say, application. The application has become easier, their effectiveness has increased, their cost has been reduced due to, let's say, the volume requirements, etc. And I can see the adhesive utilisation in vehicle manufacture continuing to rise because it's given a solution for the multi-material processes. It's been developed very rapidly, and also in terms of its effectiveness is kind of, as I said earlier, it's increased dramatically.
Yeah, it's an interesting one, that one, Martin. As you pointed out, there's a big future for adhesives. It seems to be the way to go to solve a lot of sort of solutions for joining. Right, we're bringing our Q&A session to an end now. Thank you for everyone for their questions, and thanks very much to Martin for a very informative webinar and presentation, and for answering the questions in such detail. Thanks to everyone for joining us today. The webinar will be uploaded to our archives and accessible in the future for all of your colleagues who have been able to attend the live presentation, or if you wish to revisit it. You can access this and all our previous webinars via the webinar tab on the Automotive Manufacturing Solutions homepage. If you will just take time to complete the short survey, which will appear at the end of this webinar, your feedback on these is extremely valuable to us to help us improve and bring you even more interesting topics in the future. So thanks again for joining us, and we hope you'll join us again for our next webinar. Thank you.
And thank you, Nick, and the rest of the team.